Thanks, Brian. Hello, everyone. Thanks for taking the time to attend my talk today. I'll be talking about adversarial robustness in machine learning, in particular, the importance of knowing what you don't know. And we'll see why and how abstention on what you don't know can be useful. Right, so this is joint work with my advisor, Professor Nina Balkan, her PhD advisor, Professor Aubrey Blum, and my colleague and soon-to-be Professor, Dr. Hongyang Zhang. Right. I'll pause once for questions at about half time, but feel free to interrupt me for any clarifications. With that, let's get started. Right. So suppose we have a security system, and there's a lot of controls and variables. And these controls, variables, they monitor some real quantities, let's say temperature or voltage. And suppose you ought to make a decision based on these control values. So this is our system. And now suppose there's a hacker who's trying to influence our decision. So they're working hard at it. And let's say they manage to break in and they get access to a couple of our variables. So my question is, can we still make the correct security decision? So that's a rough motivation, and with that at the back of your mind, we'll get started with more formal stuff. Right. Let me begin by defining what is classification in machine learning. So we have a set X, which we call the input space, and or the domain. And from the set X, we obtain examples. We want to classify these examples using labels in another set Y. You can often think of Y as finite or even binary. And we are interested in learning this output classifier H from X to Y, which is up to which belongs to some hypothesis space H. Right. We want to. Our goal is to minimize loss L, which we define as the expected value of this quantity, small l of y and hx, where x and y are drawn from some data distribution D. So roughly speaking, L is supposed to penalize us for whenever our hypothesis h of x differs from the true label y. Right. This is the standard definition. We also define adversarial robustness. So what's happening here? So in this case, we allow the inputs to be perturbed by the adversary. Right. So basically, the adversary can move the input slightly to a hard instance for the same label. What do you mean by hard? It's basically the goal of the adversary is to make our classifier fail on the modified input, and in order to do that, it moves the point x to a point a of x. Right, and the loss function is the same as before, except that now we have the h of x replaced by h of a of x. Right. Right. So the point is, even if our classifier was good without the unperturbed inputs, it's possible that with the adversarial perturbation it can be particularly bad, and this is observed in practice for example for deep nets, etc. Right. So. Yeah, so the question is, can we simultaneously minimize the natural loss L and also the adversarial loss LA? The idea being, and this is what we call as the robustness guarantee of our hypothesis H. Right. So there's extensive empirical and theoretical studies being undertaken these days to basically to understand this question, and a lot of different adversarial models being proposed and studied for this problem. Right. There's another definition I'd like you to look at, and that's classification with abstention. So what's happening here? We modify our problem slightly. We keep the same examples and labels, but we change the output classifier now to have an ability to abstain or refrain from prediction for some examples. Right. So there's an additional sort of pseudo label, abstain or don't know, and our goal really is to now minimize this sort of modified objective where we have the loss adversarial loss being computed only when we do not abstain, and there we also pay some price, some reduced price for the case where we do abstain, right? So there's the probability under D, which is the natural distribution of our hypothesis abstaining, right? So this is scaled up by a cost of abstention C. So for example, there are two classes. You really want C to be somewhere between 0 and half, because basically it should be less than half, because with the loss of half, if you actually can just do a random guess and still get so you basically never abstain, right? Okay, so yeah, let me just motivate the abstention a little bit more to see why it's an interesting emerging topic. It's basically it's a weaker assumption than the other assumptions like wide margins or absence of any hard or noisy examples, and yet it gives very strong guarantees. So it's known in the adversarial setting. Our work is an example. There's also a work by Shafi Goldwasser and others. And then there are a ton of other machine learning applications where this is seen. So essentially, it can get us faster convergence rates in passive learning. We can get lower regret in online learning, and also fewer labels in the active learning settings. Yeah, these are probably interesting only if you're familiar with the machine learning background. But yeah, but the idea is it's getting very popular in the learning theory these days, right?
So Dravyansh,
yeah.
So when you say it's a weaker assumption, is that like a technical notion of weakness?
Oh, no. Yeah, that's an informal notion. I should have clarified. It's really just weaker in the sense that it's something that's more likely to make sense in practice than yeah. I mean, yeah, it's an intuitive notion in the sense that requiring absence of hard examples does not occur in practice, but just modifying your objective and trying to learn where to abstain is a sort of yeah, it's a sort of different, not really an assumption, a different formulation, which is more practical, is what I mean, actually.
Yeah, maybe we can discuss why it's more practical some other time. I don't quite see.
Yeah. Okay.
I have a quick question too, Dravyansh. Do you mind just going quickly to the previous slide?
Mm-hmm.
So why in the loss, why are we kind of mapping X through the adversary's perturbation in the kind of first summand, but not in the second summand?
Right, that's a good question. So in the second summand, we just have we consider so basically the adversary tries to perturb. We are fine with it perturbing, and then if we catch it and we abstain on it, we are completely fine with it. So when we talk about the adversarially perturbed distribution, we only focus on the loss, but we don't want to abstain too much. So in the sense that in the normal case, when there's no adversary, we don't want to just abstain all the time, and then so just trivially get away with no protection against the adversary.
Okay, thanks.
Yeah. Okay, so back to adversarial robustness, right? So the question that I haven't still answered is what does the adversary A look like? A very common and popular assumption is to consider an Euclidean space X, and the adversarial perturbation A of X is at some point in the LP ball around X for p greater than 0. So basically, it can be, you can allow small movements of X in any direction really, but as long as the magnitude is not too large. This is what a lot of people use, but there are some issues with this. So and it basically does not capture many relevant perturbations, and I'll try to give some examples. Right. So for example, if you just modify, let's look at images for concreteness. So if you modify a few pixels, yes, by arbitrary amounts, the class of the example shouldn't change, but it's beyond the LP ball. And similarly, if you rotate or change the camera angle, etc., there are a ton of ways in which you can go across the LP ball, and still there are reasonable ways in which the adversary can change your input and cause you to fail. Okay. So we clearly need beyond LP norm models, but unfortunately, it's very hard to obtain low robust error in general. Right. So there's this lower bound where Adi Shamir and others show that even when you alter few image pixels, so this is the first example sort of I was giving there, it can be impossible to defend against adversarial attacks in the neural networks. They actually construct an adversarial algorithm which sort of breaks the neural networks with few pixel changes. And yeah, in general, I think it's just a very hard goal, which is one of the reasons why people haven't looked beyond LP norm models, in my opinion. Right. So now that I'm motivated beyond LP norm models, let's try to come up with a reasonable one on our own. Let's see, let's try to motivate it. So typically, classification involves embedding inputs X into a feature space F. Right. So what I mean is you for example, a deep net, you could use a deep net or some sort of embedding to map the inputs into a space where essentially the inputs gets well separated. And now once they're well separated, you've learned this complex map. You can just apply simple decision boundaries to separate out and get good accuracy, at least on the unperturbed examples. Right. One of the things that you might note from this picture is that things might not be well separated in the input space. And in order to move to the feature space and separate things, you really probably cannot do without making large movements, or basically a non-Lipschitz mapping between inputs and feature space. That's sort of the idea behind this picture. Essentially, that means small movements in the input space can cause large movements in the feature or output space. There are some exceptions to this. People have tried making neural networks or other models more Lipschitz, but with limited success, and I think I sort of motivated by. Right, so just to reiterate, we have small changes in the input space, which look like large changes in the feature space, and the way we will in particular abstract it is in the feature space, we will think of low dimensional, since the input space is smaller than the feature space, we think of low dimensional movements, basically of the dimensionality roughly the same as the input space. The adversary basically moves along these low-dimensional subspaces of the feature space. It could be arbitrarily large amounts because the network is Lipschitz, non-Lipschitz. Right. So with that motivation, we can formally define a model. So we consider adversaries restricted to a random linear subspace of small dimensions. N2 relative to the feature space, and one. Why linear? Well, just to get a start, because in general it doesn't need to be linear, but just to have a starting point. Right. But we do allow unbounded changes within the subspace. Okay, so if you're familiar with smooth analysis, I'll give you you sort of probably recognize so similarity, but just to give you a quick detour of what that's about. The slide's stolen from Dravyansh Sharma's tutorial. So basically, smooth analysis or smooth complexity is essentially something that tries to get the best of worst case and average case by perturbing the input a little bit and sort of looking at the worst case on the perturbed input. Right. In our case, it's actually a little bit stronger, even because they consider Gaussian perturbations. We actually allow, well, once we do the random movements, we actually allow kappa bounded distributions, as we'll see, and we allow arbitrary movements once the yes, we allow bounded density distributions. Basically the adversaries are allowed to create a distribution over the linear subspaces, and within this distribution, we basically apply this distribution to attack our model, and the only restriction is it's not, there's no high density points, regions of the set of subspaces. Right. And a goal is the usual thing. We want to reduce the modified loss that we talked about. And in particular, this means reducing two quantities. There's the goal one, which is reducing the error on the or the loss on the adversarial perturbed examples. And the second goal is to reduce the abstention on the natural example, because we don't want to be abstaining all the time. with that description of the model, let's start with some results.
So Dravyansh, I'm sorry, but I don't understand what the adversary is allowed to do. What's it, like a k-bounded distribution?
Sorry, a k or kappa bound distribution is essentially that you think of the set of linear subspaces of the feature space of dimension n2, which is much smaller than n1, the size of the dimension of the feature space, and let's just think of like perturbing in a random direction, right? So just n2 equals 1. So you start from a point at point x, and you're allowed to move in a random direction in the feature space by arbitrary amounts, but the distribution of these vectors is sort of kappa bounded. More generally, you can talk about distribution over sets of linear subspaces of fixed dimension.
Sorry, so what is kappa bounded?
Yeah, kappa bounded is just bounded density, right? So if you talk about the distribution over, for example, this vector Vx, the distribution over the all the directions, the distribution is kappa bounded. There's a bound on the density of the distribution. Does that make sense?
So should I think of it as the following: the adversary is allowed to pick a uniformly random direction.
Yeah, that's an example of example.
And then move arbitrarily in that direction.
Yes, that's an example. It's slightly more general than that because
so more general is fine. I'm even understanding this most basic one. Sorry.
Yeah.
So the most basic sort of thing that I could keep in mind is the adversary picks a random direction and then moves arbitrarily in that random direction.
Precisely. Okay.
Okay.
Yeah. So now we'll start with some results. We'll start with the lower bound, which basically tells us adversary the models which do not abstain are not going to do well, and the place where they fail is they cannot achieve goal 1, which was achieving low error rate on the adversarially perturbed examples, right? So yeah, our theorem is that there's at least one class where the error rate is high with a high probability. Right. Let me just explain this with pictures on a simplified example. I'll try to give the intuition for why this is the case. So let's say we have 2 classes and we have a simple decision boundary dividing the space into half. And now if you go in the random direction, you can easily, the adversary can easily succeed, right? With the probability half, you can you can always go across the boundary and cause the classifier to fail, right? But now if you try to save one of the classes, so if you save the class on the right, you would fail on the left one even more strongly, and vice versa, right? So that's the intuition why you can sort of generalize this a little bit more, and you get this sort of result, right? And the interesting thing is it even holds for n2 equals 1. So obviously it's yeah, for just moving in one direction. Sorry, a single dimensional perturbations. Right. Then with that lower bound, we will now move to upper bounds for when we are allowed to abstain. So algorithms which are allowed to abstain, and the sort of second setting we talked about, right? Modified setting. So we have a simple threshold equipped. We have a simple algorithm, and let me just go over it piece by piece. It's got a couple of parameters, but it's basically a sort of some tweaks on the nearest neighbor algorithm. Really. Right, so we have 2 parameters, the threshold parameter and a sort of separation parameter, right? So what's the separation parameter? If the closest point, so basically we sort of delete training examples which are sort of noisy. So in the sense that if you are very close to a point from a different label, we just delete it. So for example, points which are close to a boundary, or where 2 classes are very close to each other, or they're just noisy examples. So you would just delete them. And the second parameter, it's the threshold parameter, which is the more interesting one, is where what we use to decide when to abstain. And that's simply if the distance from the nearest training point, so training point is things that you've already seen, right? And you're trying to make a prediction on the test point, x. So if there is some training point xi, which you've already seen, if it's within your threshold tau, then you would make a prediction, and you basically just predict the class of that example. Otherwise, you would abstain. So these are the two parameters. It seems like a very simple algorithm, but we can give interesting guarantees, and we see some interesting results about this. Right. Okay, so we start with upper bounding the error. So that was, remember, the goal one, where we try to upper bound the error and the adversarial.
Hey, Dravyansh, I'm sorry to keep interrupting.
And it's completely fine.
But I don't understand the algorithm. So could you, is there a picture, or is there something that you could, help me with? That'd be great.
So yeah, I guess the most important thing to bear in mind is basically just two things. One is you remove noisy examples, in the sense that if an example is close to another example with a different label, so it's sort of noisy in the sense, or very close to the boundary, so we delete those examples.
Okay. And so this is like kind of creating a large margin of some kind? Yeah,
exactly. It's like an outlier removal. Sorry, okay. Yeah, creating a large margin. Sure. Oops. Yeah, and the other thing is, where do we abstain? That's the other question, right? And then we abstain in the following way. We find a training example, or an example we have already seen. And the new example where we are trying to predict the label. So X is an example we're trying to make the prediction. If it is close to one of the training examples within distance tau, then we will make the prediction, and we basically just use the label of that example we've already seen. Does that make sense?
Right. And just to make sure, so the adversary was allowed to move arbitrary distances, right?
Yes, yes.
So I guess by moving large distances, I could always make you abstain. Should I be worried about that?
No, right? Because as I said, we care about the amount of abstention on the natural data set, and the amount of error on the perturb.
Okay. Okay. Right? Good.
Thank
you.
Yeah, sure. Of course. Right. So let's move ahead. We have a theorem for n2 equals 1, which is instructive to look at, and essentially all it says is, so suppose we have a well-separated, we assume a well-separated assumption. So there is the smallest distance between points of different classes R. Essentially, this can roughly be obtained by setting sigma appropriately, the outlier parameter, but I won't have time to go into that. But yeah, assume that there is a separation between points of different classes, and we have M training examples, then the error is at most M times tau over R to the n1 minus 1. I'll give a proof intuition in a minute, but the point is, the thing to observe is it sort of exponentially decreases with the as you decrease the threshold, and it sort of goes bad as you increase the training example. So those are the things I want you to sort of note. Right. The other we can easily generalize this. Again, there's some more complications which are not that interesting, but you get roughly the same intuitive guarantee for general N2 as well. So let's start with why things work in N2 equals 1. Sorry, it should be N1. No, N2 equals 1, right? So that's the adversarial the dimension, right? So if the so the thing to observe is the adversary is starting from a test point X, and then it's trying to basically move into the threshold tau of some training point X prime of a different label than the true label of X, right? So that's the goal of the adversary. And it can do this if the fraction of directions where the adversary perturbs is inside this cone of semi-angle at most, tau over R. Right. So we're using just simple geometry arguments. We can show that the error probability is then this quantity, and then using a union bound on the number of training examples, you get essentially get the result. Right. And this also generalizes to general N2. Essentially, you start with a random vector v1, take uniformly random v2 orthogonal to v1, and so on. We basically just are breaking down the adversarial subspace by using these vectors, so sort of like orthogonalization or something. Right, and then we basically reduce it to the one-dimensional case for each vi So a successful adversary would look like the one-dimensional case for VI when it's projected to a certain subspace. Right, and these projections sort of change distances a little bit, so things get a little complicated, but ultimately, again, you get essentially the same thing, and you again use a union bound over the n-training examples. Right, so that's a rough idea. I guess not very difficult to see. Oops. Yeah, and right, so that was our goal 1. We also have goal 2, where we want to say that the amount of abstention that we do is not a lot, right? And that's on the natural data set. That's nothing to do with the adversary. Okay, so yeah, so suppose there's let's read the theorem together. So suppose there is a large fraction of points which can be covered by some wall. So think of covering number of radius, roughly the threshold that we're using, and a lower bound on the probability mass. Then the number of examples, then with a certain number of examples, which is roughly the covering number, the order of probability, the covering number, with the high probability, we will output don't know or abstain only for a small fraction of points. Yeah, and I know that's a mouthful, but yeah, the idea is very, very simple. So for any fixed ball, if you have a sufficient number of examples, with the high probability, you would have picked some point in that ball. And if you have picked a point in that ball, basically in a sort of slightly different ball around that point, you would never abstain because you have a training example from that covering ball. Right. So that's the intuition of the proof. And well, an important thing to note here again is that it's slightly difficult to see, but so the previous thing, remember, the adversarial loss got worse. Improved. The goal worked better when we reduced the threshold. But here it's the other direction. So if you reduce the threshold, you would need more balls, or for the same number of examples, essentially, you would have higher abstention. And if you increase the number of examples, remember the adversarial loss upper bound would go high. So this is a sort of tension between the two goals, and we'll see how to resolve this tension. But I guess this is a good point to pause if there are any questions.
So Dravyansh, the first parameter dependent on n1, the actual dimension of the space, right? So even if the error is in like one dimension, the performance, I don't remember what the parameters were. It was like n. Yeah. Next slide, please. Yeah. So the in theorem 1, the error is behaving like exponentially in n1.
Yeah. So n1 is the feature space dimension, and remember we have a very large feature space.
I see.
Yeah.
So if tau is much smaller than r, if tau is much smaller than r, then this raising to the n1 is actually improving your behavior.
Exactly.
Is that correct?
Exactly.
I see.
Right. So yeah, I'll summarize it all again. So we have a random feature subspace attack model, which is beyond LP norm. And abstention recall incentivizes abstaining on some hard examples. How does it incentivize that? By basically reducing the cost for those examples. So the hard example is where we abstain. The cost for those examples becomes smaller. It becomes C, which is the cost of abstention, right? Instead of maybe putting something like half when we are struggling to probably half, we're just randomly guessing. Right, so we showed in a lower bound that no classifier without abstention can succeed in our model, and we also showed the nearest neighbor with the threshold tau can have a low error with an upper bound which gets better as tau decreases. For large tau, the abstention rate is small. This was slightly harder to see, but I tried to explain it. And can we simultaneously, so the question still remains, can we simultaneously obtain low error and abstention rate and for what tau? That's at the part of the second half of my talk. how to actually set the threshold. Right. Okay. So in order to motivate the difficulty of this problem, I'll give a very, very simple toy example where you have two classes A and B, the two values of the label y, and we have examples distributed uniformly on these line segments of length d at a distance r. Everything is along a straight line, and the feature space is two-dimensional. So this is all embedded in two-dimensional plane. Right. So with just this setting, it's very hard to compute the exact value of the optimal threshold for a given value of the sample size m and the geometry r and d and the cost of abstention c. And we have this theorem which asymptotically computes it. So there are definitely surprising things here. Number one, you might expect the dependency on m, for example, to be something like 1 over m roughly, but there's slightly different, and also we only are able to get the asymptotic value of the optimal thing and not the exact value, which is just very complicated constants. The whole idea is, again, not to worry too much about the theorem, but really just to realize that it's not realistic to expect us to be able to find the optimal threshold computationally or at least theoretically. All right, so how do we do it? So in order to do that, I'll need to take a slight detour. I'll talk about data-driven algorithm design, and it's a new way of beyond worst-case analysis. So I'll try to give some motivation and see how this paradigm works. Right, so think of hard combinatorial problems. By hard, I mean the usual theoretical sense. There is no polynomial algorithm, and right. So you can think of clustering, for example, and how would you solve them? You would, since there is no polynomial algorithm, you would use some sort of heuristic algorithms, right? So either you could use single linkage, which sort of merges together clusters based on shortest distance, or complete linkage, which uses furthest shortest distance between two clusters. It's not important, but the idea is you could sort of interpolate between two algorithms, as we'll sort of see. And right, so you have a bunch of these heuristics, right? Now we sort of change the setting a little bit. Instead of solving a single instance of the problem, we solve repeated instances. And in a lot of settings today, we don't just when we're having to solve a problem, we don't have to solve a single problem. We're working on something and we sort of get multiple instances of the problem, and usually they're coming from the same domain. Right. So we get a clustering instance on day 1, another on day 2, slightly different, but coming from the same from some distribution and so on. Right. So with this setting, we can try to interpolate between the heuristics. Right. So instead of taking the shortest or the furthest distance, you sort of use this interpolated distance in order to decide when to merge clusters, for example. Or in general, you could just interpolate any algorithms, or even sometimes you just naturally have hyperparameters. This is very popular, very common in ML, but it's true in general for hard problems. Right. The interesting part to look at now is how the algorithm payoff varies with the parameter, the interpolation parameter or the hyperparameter. Right. So we can have sharp discontinuities. That's an interesting observation, especially for combinatorial problems, right? Because think of setting the centers in the k-means style clustering, right? So if there's a single cluster that changes, the whole thing can be very, very different, can cascade into very, very different results with very, very different performances in terms of how your cluster varies from the true cluster, right? So the picture sort of looks like this. So there is this parameter row and the value, which is essentially the performance of the algorithm, right? For example, for clusters, it could be Hamming distance in the true cluster. And you basically have the two things that are discontinuous, and each piece has the piece themselves. It's not like bad everywhere. It's not like discontinuous over continuous set of points. It could be bad. There are pieces where it's good or well behaved, and sometimes even just constant. So this is kind of the structure of the problem, right? And the way we formulate our problems, remember, we had repeated instances, so we choose the optimal value of the parameter by doing an online learning of piecewise Lipschitz functions. So yeah, piecewise Lipschitz function is a common generalization of the kind of function that we observe. Well, very often the piecewise constant, but not always, and we will see shortly an example. So yeah, so on day one you receive the first clustering problem. On day two another problem with a slightly different value of the variation of the algorithm with the parameters and so on. And you want to learn the value of the parameter, which in hindsight sort of got you the best performance on average across all the instances, right? So that's the sort of goal. Why are we doing this online? And the reason is we can always do online to batch reduction to give the sort of corollaries in the distributional settings. It's sort of more general. You can there are more interesting things in the distributional setting, but at least the online learning implies something in the distributional setting. All right. So with that motivation, and also like it's sort of a natural way to look at, our formulation is sort of repeated instances, and we want to look at an online version, right? So there's prior work which tells us that in the worst case, this is impossible to learn, right? I would have included an example by the time, but basically you can construct pathological examples where things are discontinuous and the sort of performance varies in a very crazy adversarial way, and essentially you cannot get very close to the optimal value, even with learning after a lot of examples, right? But not all is lost. We have if we have well-behaved functions, right? So we formalize this by dispersion parameter, which roughly speaking is says that the discontinuities are not too concentrated in a small region over time, when averaged over time. Again, I wouldn't describe it exactly, but roughly speaking, it has to do with the smoothness of the problem, or well-behavedness of the problem. Right. We can get under this assumption we can get asymptotically tight near tight upper and lower bounds, which are something between so the regret rate is something between square root t and t, and depending upon the parameter beta, and the results are sort of tied in terms of beta as well. Right. So we have an algorithm which basically, so by upper bound I mean we have an algorithm which basically achieves a sublinear regret, and basically by sublinear regret I mean you can converge with the optimum with sufficient examples, and a lower bound which says it's impossible in the worst case to if things are not dispersed, in the worst case it's impossible to get to the optimal. All right. So with that, I'll also again give a brief related work with, and the related work essentially here is essentially the idea is you start with a hard problem, a counter problem, for example, and you carefully study its problem structure, and then with the goal of understanding the distribution of these discontinuities as a function of the parameters. That's the goal. And the way you typically go about it is you make some smoothness assumption on the problem, and under that figure out, I mean, that's if that's reasonable. And under that smooth assumption, you can show that the well-behavedness. You can sort of measure the well-behavedness as a function of that smoothness. Once you can do that, you can give these sort of guarantees in terms of as a function of the smoothness, right? So and then these gives very exciting results for very, very fundamental problems like clustering, partitioning, integer-coded programming, mechanism design, branch and bound, mixed integer programs, constraint satisfaction problems, graph-based learning. These are just works from our group. There are a bunch of other people using it for sketching, search algorithms, online matching, flows and load balancing, online knapsack and set cover, constraint optimization, etc. So yeah, my point really is basically if you think of a hard problem and if it makes sense to consider repeated instances, you can probably think of this approach. It's probably useful. It will probably give you something interesting and useful. All right. So with that spiel, I'll come back to our setting. Right. So the interesting thing now is that we wanted to remember we wanted to set the threshold tau, which was sort of the motivation. The threshold tau can be thought of as this parameter in the in the data-driven design setting. And we want to optimize the loss function, which is basically, recall it, the adversarial loss and on the basically the loss on the adversarially perturbed examples plus cost of abstention times the probability of abstention. We have this function which we want to optimize as a function of the threshold. Now, these two functions are pretty distinct. So it's helpful to look at them distinctly. So it turns out the adversarial error is a Lipschitz function. With respect to the threshold, it changes sort of smoothly. But the abstention rate can be non-Lipschitz. And then just to give a brief intuition why that's the case, it's basically because you basically think of points in a cluster at some roughly uniform distance, right? So there's a cluster with all points at a distance d1. There's another cluster with all points on an average distance, mostly centered around d2, etc. And at all these points, d1 and d2, when you cross the threshold, when the threshold crosses these values, there would be a sharp jump in the abstention based on how we defined our abstention algorithm. And again, these things are all algorithm specific, really. So remember we start with our robust classifier algorithm, and we're considering its performance as a function of. So basically, it's a parameterized family, right, in terms of the threshold, and we're considering its performance as a function of the threshold, right. So the solution, as I've already given away, is data-driven algorithm design. If the data is again, so I'm using the same term again. It's not the same kappa as before in terms of the adversaries. It's a different kappa. But if the data distribution is bounded density, then we can learn the threshold using batches of data in an online learning algorithm, right? So the part that is previous work is essentially that you can do the learning if things are dispersed, but what we essentially need to show for our problem is that if the data distribution is sort of smooth, essentially what it means is, if you can perturb the points slightly, then it shouldn't change the problem really very much. The problem is not very sensitive to slight perturbations in the exact distances between points, right? I'll give you more intuition as we look at the formal theorem and proof, but that's what we are trying to do here. All right. So this is a very big, like it seems a big theorem, but I'll go at the important stuff step by step. So, right, so we first look at, we assume tau is sufficiently small. If tau is large, really, it cannot be the optimal value. If it's larger than these things, it has to be small. That's not, and when we also assume that the data distribution is continuous and smooth, in the sense that I just said, basically, if you perturb the distances between points a little bit, it shouldn't really change the problem, right? So in other words, the distribution of the distances between pairs of points is that distribution is a bounded density distribution. All right, and it's not the same kappa as the adversary distribution. I should have used kappa prime or something. All right, so then with the high probability, you can expect the expected regret is basically sublinear, right? And there's a bunch of things there in terms of the parameters. We definitely don't have time to look at them in detail, but yeah, you basically get sublinear regret. And the main challenge or the main interesting thing here is which is something that is useful if you want to apply this paradigm to your problem is that you need to find the dispersion rate, right? And intuitively, the distance between points is a smooth random distribution. We can show that the non-Lipschitzness or the discontinuities in the abstention rate are also dispersed, right? So that's the main theorem, and it sort of depends on the nearest neighbor distribution. So you go from the distance, the pairwise distribution to nearest neighbor distribution, sort of make arguments. You also sort of need a Lipschitzness bound on the adversarial loss, but yeah, so those are kind of the main ingredients for this proof. Okay, yeah, so this is all valid and good, but there's still an issue, really, right? And that is what do we have so far? We say that we have an algorithm which has these parameters, and we call it the robust classifier of threshold tau, and we tell you that essentially, by this data-driven design, we can set the parameter tau, which is close to the optimal value of the tau parameter optimal value. So, but still interesting. But it's not clear whether these dispersion conditions or these assumptions sort of actually hold in practice. So we also did some experiments, to get since learning people are more excited by experiments anyway. And we found this sort of technique, which is very similar to the ideas that we have here. So I'll briefly explain what it is. So typically when you're doing learning, you would start with an input space, which is the V1 here. You would do an embedding Z, and then you would optimize the loss, which is the V2 hat. So the red dot indicates where you're sort of doing the optimization. The optimization of the loss is based on, we're basically trying to make the labels of the predictions more accurate, right? And on the training example, we're trying to rearrange the embeddings F and G so that the loss is minimized. So we have a bunch of gradient techniques for that, right? The alternate approach is to do contrastive learning, where you start from both ends, the input space and the output space, and sort of try to maximize the contrast in the feature space, right? And this is another optimization problem which can be solved using gradient descent, etc. But really, intuitively, it highly coincides with what we're doing. They try to minimize the ratio between the interclass and interclass distances, which is very similar to our ratio of thresholds and separations. Right. So that's called contrastive sampling, and we do some experiments on contrastive sampling. Yeah, right. And we basically vary our parameters tau and sigma. And what's interesting to see here is that for the linear protocol, which is basically putting a linear decision boundary in the feature space, which is basically what everybody does with these deep networks and all these approaches. You realize that the adversary can always succeed, right? And then this sort of corresponds to our lower bound, where we say that if you don't abstain, you sort of bound to fail, right? But in our setting, we can sort of match the error on the natural accuracy. Basically, we can match the natural accuracy, get a reasonable adversarial accuracy, which is not 0, and hope that the abstention on the natural data set is not large. So the abstention on for the linear protocol is 0, but for we basically sort of trade off between the adversarial accuracy and natural accuracy by varying our parameters. Right? It's maybe more easier to see this in this plot. So we have this again. It's a one-dimensional adversary with moving points in a random direction, and we sort of plot this accuracy versus abstention. Accuracy is basically 1 minus the loss, and each curve corresponds to varying tau. Different curves correspond to varying sigma. But the point really is, on these different curves, on these curves, if any of these curves sort of find a region on the top left part of the graph, because that's where you have high accuracy and low abstention, right? And it turns out for this data, does, and by our data-driven guarantees, that implies that we can learn the optimal parameters by using data-driven algorithms over time, and with that really concludes that there is a way of setting these thresholds and the parameters where you can sort of optimize over the accuracy and abstention trade-off. Right. So that's really all I have. We have a few minutes left over for questions.
So, Dravyansh, is this can you suggest other models for this kind of adversarial robustness, which are so why is sort of this kind of model where it's smooth analysis plus an arbitrary amount of noise?
Yeah, that's a good question.
The right model.
So clearly it's trying to capture some things. Intuitively in machine learning, for example, you can think of changing features. Again, I'm trying to get into the machine learning motivation of it. I sort of, so in the beginning, I had this motivation of the general motivation, which is sort of outside machine learning, where you could do these things on a system. In machine learning, you can think of having an image and changing the, let's say, brightness or the contrast of the image, and you could change them by arbitrary amounts. That's still the same legal image, but the adversary is allowed to do that, and if it causes our classifier to fail, that's a bad thing. Does that make sense?
Anyways, we can discuss later on, I think.
Sure.
Cool. Thank you.